Okay, so next up we have Andrew. He will be our last official speaker. And after that, we only have the lightning talks left. Now, Andrew is studying computer science at the University of St. Andrews, and he's involved in coding and in music. In his free time, he experiments with electronics, climbs things he probably shouldn't, plays Edinburgh's public pianos, and dives into his passion projects. And for the last year, he has been doing music programming, very exciting. And that's actually, he's here to talk about live audio synthesis with Synchrotron. So let's just hope everything gets set up. There's some exciting stuff going on. How has it been so far? Have you liked this more technical side of things? Give me a woo. Oh, nice, thank you. I was worried of doing this kind of stuff with an Estonian crowd because I was thinking there's gonna be total silence. So thank you for the woo. So as soon as Andrew has been set up, we can do this. We do have the lightning talks, so be here for those. I think we're completely full with the slots. I think they added a slot. Not sure if it was an official addition or not, but let's try to do it. So I'll ask the organizers if it's okay. I hope it is. And after that, just closing remarks. And I do hope you have enjoyed the last few days. And you'll come back maybe next year, maybe even the year after that.
We have got a display.
You do this.
Audio.
Yeah, okay, give it up for Andrew.
Alright, hello everyone, I am Andrew, and what I mainly do in my free time, as of the past year and a half, is work on music programming. So I like code, I like music, and I thought, you know what, let's smoosh them together. But first off, I do have a question for the audience. Let me just get this running. Okay, who here knows what that logo represents? Nobody. That's, oh, one person. Wow, okay. This is the logo of a framework called Juice, spelled J-U-C-E. It's written in, I believe, C++, either C or C++, and it is kind of regarded as the standard way to make music plugins. If you want to make a virtual instrument, that is what people generally use. Why do people use that? Because everyone else uses it, because it's fast, because it's the standard. So, building off that, normally, the complaint that people have when it comes to doing anything related to live audio in Python is people say, Python is slow. We shouldn't be using Python for that sort of thing. But I'm going to make the claim that Python is actually good enough for a lot of music production, a lot of audio processing, and I claim that people should use it more. Nice. After all, we have bindings for C libraries. We already do this for a lot of things. We've got NumPy, which does all of its maths under the hood in C. We've got PyAudio, which is capable of interacting with a library called Port Audio, which gives you low latency access to directly write to the speakers on a computer. And we are already using Python for all sorts of purposes, such as data science, AI and machine learning, computer vision. So why not audio as well? So first off, I'm going to make a claim that audio programming is just data science. This is a bit of a bold claim. I'm just going to be a bit hand-wavy here and say, it's more or less kind of the same thing in a way. So to try and justify why I'm saying this, let's talk about strings. So who here knows what a generator function is? So that's about half the audience. I'll quickly run through it. So a generator function is just a feature in Python which allows you to create a function that keeps on giving. Rather than returning it and then that's it, you're out of the function, it can just keep on yielding more and more values. Thank you. it can keep on yielding more and more values so that you can have a function that generates an endless stream of data. As one quick example of this, let's consider this code here. We have got this generator function on the 3 lines which define a generator called traffic light, and you can see that instead of a return keyword, it uses a yield keyword. That's just saying that after it yields a value, you can come back to that same generator function and tell it, hey, give me the next value. So this generator is going to give 4 green lights, and it's going to give 4 red lights, and it's going to give 4 green lights, and so on to infinity. And if we then instantiate that generator and call it source, we can now print data from it using the built-in next function, which is going to keep on getting the next value. And this altogether is going to look something a bit like this. Oh, the screen is being a bit funky there on the right side, but I'm going to pretend I didn't see that. And where this gets extra exciting is that you are able to essentially manipulate that stream before it's done and running. One way which you can do this is create another stream, sorry, not another stream, you can create another generator function which wraps around this generator function and does some sort of modification to it. So this is where pipelines come in. If we take that previous code, we can now create another generator called add yellow light, which in the simulation of a traffic light, we're going to be reading values from that source generator that we give it. And then what it's going to do is that it's going to check if the new value that it got from that source is different to the previous value. So if the light has turned from green to red or from red to green. If it is, it's going to replace one of those traffic light colors with the yellow color. And now, when we instantiate traffic light, we can wrap around that another generator, which is the add yellow light here, which is essentially going to modify that stream. And the important thing is that it's not doing this before it gets any data, it's doing that while it's getting that data. The computation only happens when that next function is called. And if I run this, you can see that instead of outputting 4 green lights, 4 red lights, and so on, it's now inserting 1 yellow light instead of the green and red lights when it transitions between the colors. Anyways, this is a very cute example and all, but let's move on from traffic lights. We can do the same thing with audio, probably. Or can we? Because with audio, there is a catch. I'm going to make that a bit bigger so you can see that. The limit of human hearing is roughly 20 kilohertz. That changes a bit with age. As you get older, generally that limit frequency decreases. There's this thing called a Nyquist frequency, which is essentially the lowest sample rate you need in order to be able to represent a waveform up to a maximum frequency. And some old mathematicians who did all sorts of digital signal processing stuff that goes way over my head, one of these people, Nyquist, discovered that the frequency you need is double the limit of the frequencies I want to represent. So in this case, we need a minimum of 40 kilohertz in order to be able to effectively record human hearable audio without losing some sort of quality. So as a reference point, the quality that is standard for a CD, the sample rate is 44.1 kilohertz, meaning you've got 44,100 samples every single second in order for you to be able to hear the audio in its quality. That means that you have one sample every 0.02 milliseconds, which is not a lot of time. And the majority of programs you write are not going to be able to keep up with that. And this now doesn't even matter if you're using C, if you're using Rust, if you're using Python, whatever you're using. If you're doing some sort of processing, at some point, your program is probably going to lag for more than a 50th of a millisecond. So the solution to this is buffers. Instead of processing samples one by one, I'm going to process samples in chunks. So I can declare, for instance, an array of 100 samples, or 128 samples, or 1,000 samples, and say, I'm going to do processing on all of these samples at the same time so that the loop needs to run less fast. And now we have this trade-off where the longer the array is, the better the performance will be. Because if you, let's say you're trying to amplify a signal, you want to make it twice as loud. You need to multiply every sample's value by 2. Now, if you have an array of 1,000 values, you can do that multiplication of all 1,000 values at the same time. If you have an array of 10,000, you can do all 10,000 all at the same time. And obviously, the longer the array is, the more time it's going to take to compute. But it's still faster than running a loop and doing it on each individual sample. And the opposite trade-off is that the shorter your array is, the lower your latency will be. Because if you have, let's say, a really huge buffer size of 44,100 in length, that's an entire second of audio. That means that you need to wait to generate this entire second, and then after you generate that entire second, you can then play it. That creates this extra latency, which means that if you are taking in live audio from a microphone or from a keyboard, you're going to have to wait 1 second between you pressing the key and you hearing the sound. So we want a trade-off, which is somewhere in between that. For example, one quite common buffer size to have is 128, which if you're operating at CD quality of 44.1 kilohertz, turns out to be around 2.9 milliseconds, which is much, much more realistic for Python and C and older programming languages. Having a loop run once every 2.9 milliseconds is actually achievable. So, with all that out of the way, we can actually implement this using NumPy, because Python lists are still kind of slow. We want to delegate as much of this to C as possible. And NumPy has this feature called broadcasting, which means that you can do something like take an array, multiply it by 2, and NumPy will handle distributing that operation or broadcasting it across each individual element in that array. And it'll do all that in C, outside of Python land, where things are really fast. And that means that we can just do the maths required for all sorts of audio processing at a much faster rate. Now for the scary part. I realized that was a very short talk so far. That's because I have decided to allocate the entire remaining duration of this to a live demo of a project I've been working on called Synchrotron, which does all of this live processing. So, here we go. Time to see if this is going to work. Alright, here we are. So what I have here on the left side is UI, just a website which allows me to interact with this backend here. This is the Synchrotron server. It's written entirely in Python, and this is where the audio is actually going to come out of on the right here. On the left, I am able to type in commands which are going to instantiate what are called nodes. These nodes are equivalent to the generator functions shown in Python earlier. For example, I can say new sine node, and this is going to create this node over here, which takes in a stream labeled frequency and outputs another stream labeled out. And on its own, it doesn't do anything. Where things get more interesting is if I link it to other nodes. So I'm going to create 2 more nodes. One of them is going to be just the constant value 440, and one of them is going to be a playback node. So now with these 3, I am going to control how the data flows between these individual nodes, where this generator is just producing a constant value of 440. So it's producing arrays of length 128, where every single value in that array is just the number 440. And 44,100 of these 440s are going to flow from here into this generator here, which is going to take that as a frequency and output a sine wave at that frequency. And I'm going to say, play that to the left and right channels of the speaker system. Now let's see if I have the right speaker selected. Is this going to okay then? Let's see. Oh, there we go. Which produces a sine wave. This is, I believe, an A4 note at 440 hertz, and by itself it's not very exciting. However, this input over here, this 440, that is dynamic as well. So currently, we're looking at this and thinking, oh, it's just a number. But this is also a stream, just like everything else. And as with all other streams, we can modulate it. So what if we decided to replace that instead with another sine? I'm going to create a second sine wave. Or actually, no, I'm going to create a square wave to make things a little more exciting. A square wave, unlike a sine wave, is simply going to just go down, up, down, between the values 1 and -1. And instead of having it go between 1 and -1, I am going to make it, let's decide to offset that by 200. And I'm also going to add in a couple of other nodes here, which just do basic arithmetic operations, in this case addition and multiplication. If I was to peek into the source code here, under data.py, here is where the add node and the multiply node are defined. You can see that with this example of addition, it's taking 2 inputs as a stream and it has 1 output here as a stream. And then you have this render function, which is what is called every single time one of these buffers needs processing. This is equivalent to having that generate a callback, which is called every time you need to yield the next value. And what I'm saying on this line here is take this output and write to it to the value of the input A plus the input B. And the multiplication, it's the exact same thing, except instead of addition, we've just got multiplication here. And again, all of the maths here is handled by NumPy behind the scenes. If I was to look at the value of the stream input, for instance, you can see that behind the scenes, it is a NumPy array with a float32 type inside of it. Oh, I've made a typo. What did I call that? I typed square wave instead of square node. Now I'm going to take these nodes here and slightly reconstruct the graph that we have. Because at the moment, we just have that sine at a constant frequency. I want the frequency to be dynamic now. So I'm going to say, take the square wave, which is going between 1 and -1, and multiply it by 440. This way, it is now going between 440 at the top bound and -440 at the bottom bound. Then take the output of that and add 200 to it. So now at the top, it's going to be 640 at the top of the wave, and it's going to be negative 240 at the bottom. And if I link all of this up, I also need to place an input frequency for the square node. So let's just have that square node oscillate at a frequency of 1 Hertz. Do forgive me for this visual bug where everything jumps back to the middle. That's not very helpful. As you can see, this is still very much in development. It's not a polished product, and you would not believe how long that bug with all the nodes jumping back to the middle has been going on. I haven't quite been able to figure out what's causing it yet. I'll get there eventually. And now we have this really, really annoying fire alarm sounding tone, which is oscillating between two different waves. But we can do more with this. Because currently, having this being static isn't very interesting. We want to also be able to read information from the outside world. For instance, if you're a musician, you will want some way to control an instrument musically, probably on a keyboard. For that, there is a protocol called MIDI, which is a standard way of having note data be communicated electronically. So MIDI is a way that a drum machine can talk to a digital audio workstation. It's a way to keep different synthesizers in sync. It's used for lots of things. It's a very cool protocol. It's also somewhat complicated, and I haven't quite gotten to the bottom of it, but this can also read MIDI input. So what I will do is I'll take the synthesizer and use it as a controller. I'll plug it into my computer, and now I will try to load up a MIDI example. Once again, you have nodes scattered all over the place. So what we can see here is that we have the number 1 flowing into this MIDI input node here, and we are selecting port number 1 over here, called OP1 MIDI 1. That is this keyboard over here. And then we are taking that data, that MIDI data, and inputting it into this monophonic render node. And what this does is it takes in MIDI nodes, which are these serialized packets that say, note number 63 has been pressed at velocity 127, and just turns it into a frequency, for instance, 442 Hertz. Then that, as before, is being passed into a sine node, which is being played out. If I start this graph now, and turn the volume up, I now have this simple sine synthesizer which is controllable from this keyboard. And now I have an instrument, admittedly a very, very primitive one. This existed midway through the 20th century. Actually, no, it existed before that. Way cooler things existed in the 20th century. But we can continue to build on this in the same way that we did before. One example of a way in which we can do this is using, which one here would be a good example? Let's take the sound font example here. There we go. This time the node's loaded correctly, fortunately. So the new contender here this time is this rather complicated looking node over here called the sound font node. And in short, a sound font is just a way to have a bank of a lot of different sounds that you can load in and then play as samples. So in the same way that a regular font on a computer would contain a lot of glyphs, a lot of characters that you can draw to the screen, a sound font is the same thing for audio. So inside of a sound font, you can store a piano sample, a bass guitar sample, a drum kit, and so on. And then, as it receives MIDI data, those MIDI notes are mapped to individual sounds at different frequencies. So I have here selected a piano, which is preset number 0, and I'm also putting in the file sm64.sf2, which is the path to a sound font file. This one specifically is one that has been ripped off the game Super Mario 64 just because I like the sound of the instruments from it. And if I now start this graph here, we now have a slightly quiet but functional piano. Let's see, where did my sound mixer run off to? I can't figure out why my sound mixer isn't launching, but I'm not going to worry about that for now. And I can change this preset by mapping in a different input to this preset here. So for instance, I can take this percussion value and pass it into a preset here. And now I have percussive sounds. And notice that I did not need to restart the server, nor did I need to tell it to reload the sample. I could even switch the file to be loaded. Now I'm using a different sound font. And the sound changes. And behind the scenes, this is why Python is actually a surprisingly good choice for this sort of audio work, because you can do a lot of this hot reloading stuff, where you just hot swap different parts in and out, and everything else just works. There is no need to recompile, which you need to do with Juice. There is no need to even restart the server. You can play around with the parameters, tweak settings as you wish, all in real time. And as a further example to expand on this, I'm going to now take that same MIDI output data here and route it down here to this monophonic render node. It's the same thing as before, it's just playing a sine, except this time I'm adding the two sources together. I'm taking that sound font and adding it together with this sine over here, and then combining the two into an output. Change this back to a piano. I'm not sure how audible that is for everyone. But that is the sine wave being generated down here in combination with the sound font up here. And now to build on this even further. Let's see where I save this. That's where it is. Things are getting really, really complicated looking now. So what I have here, I'm going to take this piano sound, map it to the sound font, and now what is going on all the way over here? We're starting to introduce music theory now. Over here, I've got a chord node, which takes input data, which is just a string describing different chords. So this one here is C minor 7, and that is just an absolute chord. It's saying that this is a chord built on top of the note C. And this here is a relative chord, where it's saying note number 1 in Roman numerals, because musicians decided to be a bit strange. And again, it's a minor 7 chord. In the key of C, chord 1 would be the note C, so these two are currently equivalent. And this is being passed into this chord node, which reads that string and uses a Python library called Mingus, which converts this into individual MIDI notes. Those MIDI notes are then being passed to the sound font. The output of that is being multiplied by 2 in order to make it louder. And then through this routing chain, it makes it to the speakers again. However, this time, I'm not going to trigger this with my synthesizer. I'm going to program it in a pattern, and the way I'm going to do this is using this trigger node here. As an input for this, I have got this square node here, which, as before, is just going to be a signal that jumps between 1 and -1 up and down, and it is going to oscillate at a frequency of 2 times per second. So that means that this chord node should play a C minor 7 chord twice a second with the piano sound, multiply the volume by 2, and then route it to the speakers. If I hit start, that is exactly what we get. And again, all of this can be modified in real time. I can decide to change the key to D. I can modulate up. And now everything has shifted up by a tone. Again, I can go back down. And now I have a very, very rudimentary way to program in a chord sequence, for instance. And this can be taken, yet again, even further. Currently, this chord is completely static, which is a little bit boring. What if I was to generate something based off the chord that is being input? One way that this can be done is what's known as an arpeggiator. Now's the part where I see if I can get audio from this running into there. Let's see. There we go. This is a Pipewire patch fade. This is not part of this demo. This is actually what's going on behind the scenes on my Linux computer, which also uses a very similar patch fade UI. You can probably tell where I took inspiration from. So what I'm going to do is I'm now going to say, take the output from my synthesizer and route it to this audio expansion card. So let's take that and route it to there. Hopefully, if I now go to the synthesizer here, there we go. I now have audio output from the synth. Now I can hold a chord down, and it will just sound as a chord. However, many synthesizers have a feature called an arpeggiator, which simply iterates over the notes that are being held down and plays them in sequence, in a loop, forever. So when I hold down a chord like this, it's going to simply play this. And if I enable the arpeggiator on this synthesizer, if I hold down a single note, it's going to play that note on repeat in a really annoying way. But if I hold down multiple, we have an arpeggiator here. So now, let's make our own in Synchrotron. I'll take everything that I've got here and delete it. I'm now going to try starting from scratch. I do not have a preset for this, so now we are going into dangerous live demo territory where I am doing something novel. So here is a feature that I have managed to bung into my source code, I believe, yesterday night. Let me see if I can find the arpeggiator. There it is. This here, as you can see, I've got a little comment here. This was actually generated. This was one shot using Claude Code. I am not sponsored by Claude Code, by Fantropic in order to say that. But yes, it was surprisingly good at understanding my source code and simply banging out this node over here. And over here I've got an arpeggiator node. which is going to look at the notes being held down and append them to this list here. And then upon rendering, it's going to iterate over the input in MIDI and look at which notes are being held down. The way it's going to do that is check if the opcode is note on. If it's on, then it's going to append that to held notes. And if the note is, if the signal is note off, meaning the note has been released, it's going to remove that. And then it's going to simply iterate over the current arpeggiator note. And here's where the, let's see, where is it? There we go. Here's where the iteration happens. It is going to iterate over those stored held notes, and it's going to play them in a sequence. And the way it's going to know when to play them is that, just like the chord node, it's going to take in a step parameter, which is going to enforce when that's triggered. Hopping back to here, I'm going to want myself an arpeggiator node. I'm going to want port 1, and port 1 is going to go to the MIDI input node. What's it complaining about? MIDI arpeggiator node. I need a title again. So now I am going to take this here and take that number 1. I'm going to say that is the port I want for a MIDI input. And then the data here is going to go into the notes for this arpeggiator. Then that arpeggiator is going to go into a sound font node. Oh, it's doing the annoying thing again. I'm going to see if I can actually kill the server and restart it to hopefully not have that bug come back. There we go. And now I'm going to take all of this, pop it off to the side, and retype that. Or I'm going to reuse this MIDI input here. What I want is, I want to add an arpeggiator. There it is. And I'm going to pop it in between the sound font here and this MIDI data here. And now I can choose to trigger it using a clock node. This clock node here simply takes in a frequency, and just like the square wave, it goes up and down, except it generates these little spikes in value. So it's 0 all the time. And then if the frequency is 1, then once a second it's going to produce a single sample with a value of 1. And this is going to be how I communicate to this MIDI arpeggiator node that we want to step onto the next node. And if this sounds really hacky, first of all, it kind of is, but second of all, this isn't something novel. There are these weird, wacky, and wonderful things called modular synthesizers, which are real-life equivalents of what I've got emulated over here, where we've got all of these catch cables connecting different modules, and these modules send control voltages to each other. And because it's all analog, the only way you can communicate is using spikes in voltage, so everything is encoded into just a single stream of data. I'm doing the same thing here with this clock node. Well, I'm doing the same thing with everything here. Everything here is just a continuous signal. And I'm going to say, let's input a frequency of 2. So I'm going to take that value 2. Let's move everything back up a bit. I'm going to take that 2, feed it into the clock node. And now if I hit start, just disconnect that top branch for now, I should hear nothing. But if I was to hold down a note here. That buzzing is probably not very helpful. I now have an arpeggiator that is no longer running on this synthesizer here, it's instead running in Synchrotron. And if I hold down multiple notes, now, at this point, you might be thinking to yourself, okay, this is quite a cool toy example, but why would you choose to use this as an instrument over just buying a synthesizer like this? Well, there is one answer I can give, that being synthesizers, there we go, tend to be rather expensive. That's not a very accessible price tag. Now, more than that, this, albeit it's a bit messier to use, it's less refined at the moment, this is a lot more powerful than a synthesizer like this, because I can now chain stuff in parallel. I can add processing in the background to do whatever I want. I have this chord here, which I'm going to plug back into here, which currently is running a percussion preset, which is playing a cowbell sound. And this can happen at the same time as I play something else. Now, before that gets annoying, I'm going to disconnect that again. Or what I can do is I can take this MIDI input and route it to multiple places. So what I have here is, again, a monophonic render node going into this sawtooth wave. And now I can have which is novel. I created this on the spot, you all saw me do this, and you don't have to go and buy dedicated hardware that is capable of doing this one really niche thing that you wanted to do, for example, play a sawtooth at the same time as having an arpeggiator run through a sound font. You don't have to have a lot of different software and pre-program it in a DAW. You don't have to compile programs in a framework like Juice, or learn how to use C++. You can just write a dozen lines of Python code, or get Claude to write it for you, and then your imagination is the limit. As you can see here, Python is massive. And now, I believe it is time for questions.
Yes, thank you so much. It seems like so much work has gone into it, and like you even finished up some stuff for the demo last night, so thank you. There is a few questions. So, for example, is it possible to add a microphone as the input to this post-process the sound?
Yes, it absolutely is. I have not done so yet, mainly because I don't actually have a high-quality microphone. I have my laptop mic, and that's not great because it's going to end up with feedback loops. But if I go to audio.py here and go to this playback mode, let's see if I can find it. Yes, here I am using PyAudio, and it says here simply get default output device. I can just replace that with get default input device, and then I'll have a stream that's going the other way. Instead of writing data to a speaker, I'll be reading data from a microphone. So this is very easily doable. I just haven't gotten around to it because in my specific use case, I have yet to get a good microphone for that.
Okay, so what about taking an actual song notes as input. Is it doable in theory? Maybe, I'm not sure what they meant here about song notes, but...
It's not just doable in theory, it is doable in practice. I do have various I.O. for reading and writing to files implemented here. For example, I think, is it a live file node? No, I'll check my source code. Oh, WAV file node. So you can, for example, write to files. You can also implement nodes which do things like reading from files. MIDI isn't just a format for live communication between devices. You can also get MIDI files, which are essentially files that contain serialized data about what node is triggered and when. So you can take that as an input, as a node, into Synchrotron, and have it play from that file using whatever sound you want.
Okay. There is some good questions here. I think you can answer them on Discord because I think we should go for a coffee break now. Otto, your question, you have answered your question yourself actually. I was reading it here and it seems like that question has already been answered. But Andrew, thank you so much for all this work and this great demo, and I hope we keep doing this.
Thank you.
Give it up for Andrew. By 15:40, and we are starting then with the lightning talks. If you have registered for the lightning talk, please stay here. We'll do like a little bit of a tech rehearsal and get the things going. So yeah.